Okay, here we go. Like I said, whoa, it decided to do some sort of update. No harm, no foul. As you may know, we have a test on Tuesday. So test number 2 on Tuesday. We're getting there. We're going to do a review of chapter 7 today. And I posted the questions that we'll be working through, but I wanted to give a brief outline. I'm pretty sure it's in one of the practice for the test somewhere, but just as an outline, the test 2 is going to be 4 long answer questions. Okay. 4 of those potential question types, right? And when I talk about the question types, really what I mean is which section on the formula sheet are you working in, right? 1 sample proportion, 2 sample proportions, chi-squared goodness of fit, chi-squared test of independence, 1 sample mean, paired data or matched pairs if you prefer, and then 2 sample means, right? Those are all the different types of questions that I could ask you. But on the test, because that's way too many, there will be 4. Okay? 4 long answer questions. Then, do you guys know what a mad minute is? I don't think they do it in elementary schools anymore because it's cruel. But when I was in elementary school, I think like grade 4, we would do mad minutes where you do like 100 multiplication problems in a minute, 100 addition, 100 subtraction, and it's just like to drill you. So we're going to do a mad minute for question types, but not 100, only 5. But it does involve just reading the question, and then all you have to do for 1 mark each is just tell me what type of question it is. Okay, and so just be prepared to identify what type of question you have. Okay, and so then 5, I'll just say read the blurb. Is that a real word? Read the question, I guess. It's not a question though, you don't have to answer it. So that's why I'll call it a blurb. 5. 5, read the blurbs and say what type of question it is. Just 1 mark each. Oops. That's going to be nice, or nice to have seen lots of different question types for the final exam, right? Same thing as test 2. The questions won't be in order. You have to read them and figure out what type of question you have, and then go ahead and answer it, right? That takes practice, but once you've decided what type of question you have, then how you solve it is always the same. And so from there on, I kind of just assume that you can do it. Okay. Good. Any questions about the test on Tuesday? All right. Then let's get cracking. I'll move this up then. So I posted inference for numerical data practice or something like that on Moodle. And so these are the questions that we're going to work through. I will say that you may assume the conditions for inference have been satisfied for all of these, because otherwise we're just going to waste our time checking the conditions. Yeah? So, good. So This is from an old test that I had made once upon a time. But it's a platypus test. And platypus doesn't start with M, and so it got cut, and now it's just for review. But I feel like my tests used to be way more creative. Now they're kind of simplistic. But in italics are just some platypus fun facts. You don't have to read it, but it does kind of set you up for the rest of the question. And then the question is in non-italics. What I want to do is just go through each question, read it, and talk about what type of question it is, right? And then we'll go back and we'll do it. Now, from experience, and I dare say I have a lot of it, especially because I made this question. I made all these questions. Just looking at this table, right, I suspect that it's going to be a paired data type of question. Why? Because I have the mean and the standard deviation of the differences. The only time I would really need that is if I have paired data. Okay, and so that's a nice clue, right? And so here I'll just kind of make a little note to myself, right? Paired, maybe? We'll read the question and convince ourselves that it's paired data, right? But that's going to be a really nice clue. If you have a table like this, and I give you the differences and the mean and the standard deviation of the differences, then it'll be paired, okay? So let's read it and find out. Oh yeah, so a platypus, hopefully you know what a platypus is. They're like this hodgepodge made up animal. They're not made up, they're real, but the males are venomous. And so they have sharp stingers on the heels of their rear feet, and can use them to deliver a strong toxic blow to any foe. How dramatic. Here's the question. You overheard some people talking, and they were saying that the platypus releases different amounts of venom if he's provoked and angry, which we'll classify as angry, than if he's startled or cornered, so we'll classify that as scared. I've made this up completely, just, yeah. So don't, there's no weight to it. That's my creative right. Naturally, you decide to test this theory with a sample of 32 randomly selected platypuses, and I did confirm that that is the plural. Although there's some debate. You could go platypi, I think, but platypuses seems to be and it sounds cuter. You decide that they will all receive both treatments. Aha, that sounds good, especially because I'm trying to talk myself into this thing being paired, right? And what's paired data? It's paired if you have two measurements on the same subject, right? And so here, they will all receive both treatments. Okay. Some will be scared first, and some will be made angry first, and this assignment will be done randomly. Oh, good. Proper protocol here. Although ethics might disagree, scaring them and making them angry, but whatever. The amount of venom secreted after each treatment is measured in milliliters, which of course is a numerical measurement. And so I have numerical data, right? And a summary of the data you collected is found below. And then we want to know, is there evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry, than if they're startled or cornered? And then we're going to use a confidence interval to test it, and then we'll do a formal hypothesis test to test it, just so you can see both. But I feel good, right, locking it in that this should be paired data. And so I'll do this. Yay. Because they both receive both, or they all receive both treatments. Okay. So for the type, this is going to be paired data, since all platypuses, and you don't need to give this last part, I just need to know what type, right? The header on the formula sheet. Okay? But I'll explain for your benefit. Since all platypuses receive both treatments. Nice. So like I said, we're going to read through all, there's three and then just a tiny follow-up question, which I'm not counting. So all three questions, and then we'll go back and do them. Similar to how you have to do it on the test, where you read a blurb, right? Figure out what type it is, and then you move on. Okay. Question 2. Someone cracked a joke saying that platypuses are even slower than manatees. The nerve. Clearly, I've used manatees. I've used manatee tests for 10 years now. It's a lot. Usually teach it about 4 times a year. Wow, it's a lot of manatees. Naturally, you decide to analyze the validity of the joke because you're no fun that way. You randomly select 200 platypuses because you want to be really sure, and you record their speeds. You find the mean speed of these platypuses to be 3.6 miles per hour with a standard deviation of 3.1 miles per hour. Clearly, I stole it from somewhere else because I would use metric, but whatever. You randomly select 156 manatees and find their mean speed to be 3.9 miles per hour with a standard deviation of 2.8 miles per hour. Now, we know that we're restricted to chapter 7, which is really just one sample mean, paired data, or 2 sample means, right? I definitely have 2 samples, right? And even if you were deciding between proportions versus means, one dead giveaway is that I give you a standard deviation, which I couldn't possibly do. I give you a mean, of course. I give you a mean and a standard deviation, but definitely the standard deviation tells me, okay, then it has to be numerical. There's no way it could be any sort of proportion or categorical data. Okay? So with these things in mind, right, I have 2 means and 2 standard deviations. I have 2 groups, and I want to compare their means, probably their mean speeds. Right? In fact, is there evidence that platypuses are even slower than manatees? Right? And so here, platypuses on average 3.6 miles per hour, manatees on average 3.9 miles per hour. Now 3.6 is less than 3.9, but we want to know if it's significantly less, right? So that's what this question is asking. But I have 2 independent samples. There's nothing that says, hey, this platypus should be matched with this manatee, right? There's no logical way to say that, right? And so for that reason, 2 independent sample means. I usually throw the independent in there just to emphasize that they're kind of separate, right? And so here two independent sample means. Oops. I think on your formula sheet, though, I just have it, yeah, two sample means. But if you want to toss an independent in there, that's cool. I do it for emphasis. So two sample means, right? Since I want to compare the means from two groups, which I'll do a follow-up here. Now, you don't have to justify which type you choose, right? I'm just doing it so that you know why. Since we want to compare the means from two groups. Okay. Nice. Okay. Process of elimination tells me what the next one is going to be, but you won't have that that perk on the test, so we'll just read it as if it's fresh. I'll kind of skip in as a platypus fun fact. So they're bottom feeders, and so what they do is they kind of scoop stuff up from the bottom of the body of water, I guess, including dirt, because they don't have teeth, and so they use just kind of gravel to chew their food, like from the bottom. They kind of like grind it, I guess. Anyways, so that's kind of a fun fact. Platypuses are really interesting, but they're also really freaky if you read a lot about them. That's not what this class is about, although it could be. You would like to estimate the mean amount of material a platypus stores in their cheek pouches. So they kind of, like hamsters, they kind of like stuff their cheek pouches and go up top and eat it. So you collect a random sample, or it doesn't say random, I read that as random, but you collect a sample of 40 platypuses and measure the amount of material each of them stores. You find the average to be 33 grams and the standard deviation to be 5.3 grams. Now, when I read this, keeping track of, okay, well, how many samples do I have? Here, I only have one sample of platypuses, right? I have 40 platypuses. I have a mean and a standard deviation. Okay? And so I'm kind of leaning towards a one sample mean type of problem. Okay? The question says, you've heard that they store 30 grams on average in their cheek pockets, but you suspect it might be more than that. Okay? Is there evidence to support your suspicions? Okay? And so now I have this one sample of 40 platypuses, and I have a mean and I have a standard deviation for them, and a number that I want to compare them to, right? All the things that I need for a one sample mean problem, which is what it is. One sample mean, since we only have one sample, and we want to compare the mean of that sample to 30. Maybe I'll keep it generic to a number. So we want to compare the mean of that sample to a number. Oh. Nice. And then, like I said, there's a little follow-up question here, a little blip. Discuss what it means to make a type 1 and a type 2 error in the previous question. And so that's just a little follow-up. But nothing to worry about. We'll get there. Okay. So figuring out what type of question you have is going to be really, really important. It's also really, really difficult, right? Takes a lot of practice. And so that's why I give you so many practice problems to read through and try so that you can start to pick up on patterns for the different types of questions, right? And so what would they look like? What are some common phrasings that I use? And so that'll be really useful, both on this test, but also, of course, on the final exam, which feels like it's just around the corner. It's crazy. Okay. Any questions before we start the actual problem? So we decided question 1 is paired data, which means when I go to my formula sheet, this here is the only region that I'm interested in, right? You can block out the rest of the formula sheet, right? Once you've decided it's paired, then you're stuck here. We can build a confidence interval. We can do a hypothesis test, right? It's got all the things that we might need. So let me just grab this maybe. And I'll bring it down here. So for part A, is there evidence that platypuses do in fact excrete different amounts, right, of venom depending on if they're angry or if they're scared? Use a 95% confidence interval to test the hypothesis, kind of a mashup. Usually, right, usually I just say construct a 95% confidence interval. And then you have to construct it and you have to interpret it, right? But now I'm making you take the extra step and say, okay, can I use a confidence interval to test a hypothesis? Test the hypothesis. Yes, you can. So here we go. We are allowed to assume that the conditions have all been satisfied, right? That's nice. Randomly sampled, right? My sample size in this case is larger than 30 because I have an N of 32 platypuses, right? Which gives me 32 differences, right? And so here I'll just jot down that N diff is going to be 32. This value here, this negative 0.5, is the mean of the differences. That's your X bar diff. And the standard deviation of the differences is your S diff. I also give you the mean and the standard deviation of the scared data and the angry data, right? Because it exists. But it's your job to know that, okay, if it's paired data, then I should be analyzing the differences. All right, let's make a 95% confidence interval. From your formula sheet, you have X bar diff plus minus T star times S diff divided by the square root of N diff. We need T star, right? I have all the other components, but I need T star, and T requires the degrees of freedom. Okay. It's actually in here in the subscript. It's NDiff minus 1 is your degrees of freedom, but it's also highlighted down here if you need it. So the degrees of freedom is NDiff minus 1. So need T star at degrees of freedom equal to NDiff minus 1. NDiff minus 1, well, we had 32 platypuses, which means we would have 32 differences. So I have 32 minus 1, which equals 31. Now, I go to my T table because I need my critical value, T star. Let's go. I try to find 31 degrees of freedom, but I'm choosing between 30 and 40, and you always have to round down. And physically up in the table, which is confusing, but you always round down. Okay? So we have 30 degrees of freedom. Now, what I want you to do, because it's your job to show me all the things that you know, right? And so if you found the degrees of freedom is 31, but then you also found that you have to use 30, then tell me that, right? But using 30, but using degrees of freedom equal to 30, we find T star is going to be what? Let's see here. We want a 95% confidence interval. Let's see if I can trace this down. I get a T star of 2.042. Huh? I'll bring this in here. Copy. Now I have all the, yeah, sorry, question.
I'm just wondering why we're using confidence interval.
Oh, because it said use a 95% confidence interval.
Oh, okay.
In part B, we'll do a formal hypothesis test. We're just getting practice with all the things. All the things. On the test, I'll only make you do either a confidence interval or a hypothesis test. It's too long otherwise. But practice with both. Okay. Now we're ready. Ready for what? X bar diff plus minus T star, I'll just rewrite it here, times S diff over the root of N diff. Sloppy, but that's okay. I have these values. X bar of the differences, I think it was negative 0.5, good. Plus minus 2.042, which we just found, times S, which is 7.51. Oops, I'll clean that up. Divided by the root of 32. A common mistake I see is that you just spent time calculating the degrees of freedom, and it's tempting to use that in your square root, but you have to just use your n. Okay, here we go. 7.51 divided by the root of 32 times 2.042. I'll just check in here. I get the margin of error of 2.710944869. which means I have, oops, negative 0.5 minus that guy puts me at negative 3.211. I'll go to 3 decimal places. And negative 0.5 plus that guy puts me at 2.661 to 3 decimal places. Because I don't want to write all those out. As a rule, you should always match the number of decimal places that you were given. Okay? And if you're given kind of different amounts, like here, these are both 2 decimal places. So you would want to give me at least 2 decimal places, right? Is kind of the broad strokes rule. Now, for practice, we're going to interpret the confidence interval, right? Just to make sure that it's the same blurb always, right? And so just make sure that it's well rehearsed, right? And so how does it go? We are 95% confident that the interval from here to here captures, and then whatever we were asked to make a confidence interval of. The mean difference in amount of venom excreted, I guess is the word I'm looking for. So now, just to show that they're attached here, we are 95% confident the interval from negative 3.211 to 2.661 captures the mean difference of venom excreted when angry versus scared. That's just your run-of-the-mill confidence interval, right? And then I've tacked on a little bit extra where we're going to check a hypothesis, right, using this interval. Is there evidence that platypuses do in fact excrete different amounts of venom? Now, if I go back to my formula sheet here, right, my null hypothesis for paired data is really nice. This is always the null hypothesis, mu diff equals 0. And so we want to test the null hypothesis that mu diff is equal to 0 versus the alternative hypothesis, which has to be about mu diff and how it relates to 0. And then from the question, we want to know if it's not equal to or less than or greater than. Now, we only want to know if there's a difference, right? Different amounts. And so I have a not equal to here. Kind of beyond the scope, but you actually can only use a confidence interval to test a 2-sided hypothesis test. Otherwise, you'd have to make adjustments, but that's beyond this course. Remember how to use confidence interval to test the hypothesis? Well, we first assume that the null hypothesis is true, right? And say, okay, well, mu diff is equal to 0. Then you go to your interval and you see that you're 95% confident that 0 is one of the outcomes, possible outcomes. And so then we do not have evidence to reject H naught, right? if this interval was entirely below 0 or entirely above 0, then you would say, hey, 0 is not reasonable here. More likely that it's not equal to 0. Right? And when we did it in the past, kind of drew a number line like this, and I put my confidence interval on it just so I could look at it, right? And then I could say, hey, 0 would be somewhere here, right? That just means that there's no evidence against H naught, right? And so our conclusion would be, since mean difference of 0, difference of 0 is in the interval, we do not have enough evidence to reject H naught. Therefore, what was the question? Oops. Eek. Don't want to do that. I'm going to cheat. Again, I guess. There is no evidence that platypuses do in fact excrete different amounts of venom depending on if they're angry or if they're scared, period. Nice. So now we already know the results for our formal hypothesis test, but like I said, on the test, I'll only make you do one or the other, of course. Any questions before we do the formal hypothesis test? We've done a good chunk of the hard work already. So now we're going to test the exact same question and use a formal hypothesis test with an alpha level of 0.05, which is our default as well. Okay, step 1, because we're allowed to assume that all the conditions have been met. Right? Step 1, state the hypotheses. We already did that, and I know it seems like we have a lot of time. There's a lot to say, so I'm just going to go for it. Right? We decided it's paired data from the formula sheet. Oops, wrong file. From the formula sheet, right, for a hypothesis test, this will always be your null hypothesis. This is also, your formula sheet is laid out as step 1, followed by step 2. Then once you have your test statistic, that'll determine how you find your p-value, and then your conclusion depends on your p-value, of course. So that's kind of as far as I can take you in terms of the formula sheet. But there's a lot of clues on there. Mu diff is equal to 0. And we said, I want to know if they excrete different amounts, which means that the mean difference would be different from 0 words. I know, gets a little boggy, but as long as you're really careful, you'll be all right. Since I have a not equal to here, I want to know if there's a difference. then I care about both extremes, right? If one is extremely less than the other or greater than the other, right? And so that's what makes it a two-sided test, which means later we'll need a two-sided p-value. Okay. Step 2, do the test. Do the do. The test is calculate a t. It's a t-test. T is equal to x bar diff. And I think I saw I have -0 on the formula sheet. I'll just confirm so it matches. You don't really need to write the -0. It's on there because we always compare it to the hypothesized value, the null hypothesized value. How far is my mean differences from 0, right? So you don't need to write it, but, and then over S diff, divided by the root of N diff. So t in this case is -0.50 minus 0 divided by 7.51 divided by the root of 32. I am pretty sure, let me confirm. What's nice is for means, right, for numerical data, the standard errors are the same for a confidence interval as a hypothesis test, which is not the case for proportions, right? So if you have it calculated already, you could reuse it. I didn't save it. It's not worth saving. It's not worth it. Okay. But now, let's do 7.51 divided by the root of 32, and then -0.5 divided by that guy. I get a t of -0.37662145547. Because we already found the confidence interval, I'm not surprised by this t, right? I would be surprised if it was kind of bigger than 2 somehow, right? Because that would contradict what we found in our confidence interval, right? But this is in line with our confidence interval. So I am not surprised. I refuse to be surprised. Add a page. So t to 3 decimal places, -0.377. For t, I use 3 decimal places because my t table gives me 3 decimal places. So I need to keep at least 3. Otherwise, you might choose the wrong side. Step 3, we want to find the p-value. Find the p-value the same way for any t that we've calculated. And so we need our degrees of freedom, and I'm going to pretend like we haven't already solved it. And so using the t table with degrees of freedom equal to n diff minus 1, which is 32 minus 1. Degrees of freedom equals to 31, but using degrees of freedom equal to 30, whew, all the things that we need to keep track of here. And highlight this 30 degrees of freedom row and snag it and bring it in. This is where I need to decide or know if I have a one-sided test or a two-sided test. So you can scroll back up, but I'm going to skip that part because we already decided it's a two-sided test. So I need a two-sided p-value. So now what do? I take my t, the absolute value of t, right, drop the negative, and I find which values does it fall between. Okay? So we won't get very far, will we? The absolute value of t equal to negative 0.377. I'll do my setup here. Even if you have no clue what you're doing at this point on the test, just telling me this is good. I'll give you a little half a mark or something. There's nothing there. I know, right? I'm so grateful for anything you'll give me. All right. We don't get very far, like I said. But remember, we do have always 0 on the inside here, right? T is still centered at 0, right? And just to point it out, at the opposite end, you have infinity. Okay. So at 0, right? Because here we find that our 0.377 would be between 0 and 0.683. So I'm somewhere between 0 and 0.683, which means my two-sided p-value at 0, right? So I'm in the very center, and I want to know how much area do I have in both the tails? Well, it should be 1, right? And so here, this would be 1. So it's between 0.5 and 1. Similarly, if you were over here, because this can happen too, and I just want to point out that you know how to deal with it, because we've seen it a few times. But at infinity, the area in one of the tails would be 0, and 2 of the tails would still be 0. Versus if I'm in the center for a one-sided p, I want to know how much area in the tail do I have on one side, right? That's the middle. So that would be 0.5, just for completeness. We have a two-sided test. So our two-sided p-value is somewhere between 0.50 and 1. Making sure you read them from right to left, because you have to list them from smallest to largest. Oh. Okay, so we've got a really large p-value, just as we expected. Right? No surprises here. We're just doing the work, which is, I would argue, half of research. Oh yeah, just exactly what I thought it was going to be. Step 4 is your conclusion. Same blurb as always, right? You have to touch on 3 things. You have to compare your p-value to the alpha level, right? What does that mean in terms of your null hypothesis? And then, of course, what does that mean in terms of the question? Yeah. So, show off all the things that you know. Since our two-sided p-value is between 0.50 and 1, I will point out that on the test, right, the conclusion is 3 marks, right? Because there were 3, I do 4 fingers. There's 3 components, right? And so 1 mark each, okay? And so it's a heavy hitter. Even if you're completely stumped, right? You don't know how to do this thing, okay? Just tell me something reasonable for the p-value, right? It has to be between 0 and 1. Those are the rules, right? And so just tell me what you're going to use as your p-value. You don't get marks for the p-value, but as long as your conclusion follows what you told me your p-value was, that's what I'm looking for. Okay? And so just pick something, follow through. I know that's easier said than done, but you have that as a fallback plan. But Emily, couldn't I just memorize a generic conclusion then? I guess. Yeah, you could. I have yet to see anyone do that, and I encourage people to do it every term, so maybe someone will be the first. Okay. Since our two-sided p-value is between 0.5 and 1, it is not less than our alpha level of 0.05, because I don't want to scroll up there, I remember, of 0.05, but it was given. Oh. Which means we do not have enough evidence to reject H naught. Which means we do not have enough evidence to reject H naught. And then same conclusion as before, which I'm going to steal again. Oops. There is, therefore, there is no evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or blah, 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 blah.
Where do those 3 marks, like,
Mm,
like specifically
good.
go?
1 mark for comparing your p-value to your alpha level, right? Is it less than the alpha level or is it not less than the alpha level, right? And I would use that distinction. It either is less or not less, okay? And then the second part is then using that, do you have enough evidence to reject H naught? Or do you not have enough evidence to reject H naught? And then finally, arguably most importantly, but I always do a cheeky copy paste of the conclusion in terms of the question, right? That's the one everyone loves to forget about. 3 marks. Everyone forgets because you've done so much work that surely you're done. But you should probably answer the question. Nice. Okay. Good. And I will say, so I mark for follow through, obviously. And so if you have the wrong p-value, as long as your conclusion follows what you found, right? And then whatever you say here, if you told me that it is less than 0.05, that's not true, so I can't give you that mark, right? But then if you say that means we have enough evidence to reject H naught, then I can give you that mark because then you followed through. And it's this nasty daisy chain of marking for me. So I have to try to figure out what makes sense. What's the next logical thing for you to say? But I will follow through. Oh. Nice. Any questions about that one? What am I doing for time? Okay. The next one, where we want to compare the platypus speeds to the manatee speeds. And we decided that, of course, it's 2 sample means. So I'm going to snag that part of the formula sheet. And that way we'll just focus here. I'm also going to jot down all the information that we're given. In this case, it's given in a blurb, right? Which can be kind of overwhelming. Sometimes I give it to you in a table, right? But a table that might look something like what we're about to make. But I wanted you to see it in a sentence, just so you'll be able to pick it out, even if there's not a table. Okay. Might have something like this. Oops. I think our first group was the platypuses. I'll do platy and the manatees. I guess I could do both written out properly. Something like this. Now I know each of them are going to have a sample size, not even necessarily the same. Right? I know that each of them will have a mean, and I know that each of them will have a standard deviation. Definitely, if you see a table like this, it will often be a two sample means problem. Right? Notice that there's no differences as well, right? No mean of the differences, no standard deviation of the differences. Okay, let's jot down what we have. We have 200 platypuses. We have 156 manatees. The mean speed 3.6 with a standard deviation of 3.1 for the platypuses, and 3.9 and 2.8 for the manatees. Okay. A lot of information here, right? I'm going to say that my platypuses, I'm going to treat them as group 1 and my manatees as group 2. The only time I need to use question-specific subscripts is in my null and alternative hypotheses. Otherwise, it's hard to read, right? And so, but otherwise, just 1 and 2 is fine, as long as you have defined them somewhere. What do we want to do? We want to know, is there evidence? Well, that's a hypothesis test, isn't it? So on the test, I don't tend to say use a formal hypothesis test, but I would say use an alpha level of 0.1, right? So maybe I'll scratch this out. Or maybe use an language, an alpha level of 0.1. That's how the question would read. But is there evidence means that you have to do a full hypothesis test. Also, the number of marks kind of gives it away too. Okay. We are assuming that all the conditions are met, right? But we sampled all our manatees randomly and platypuses randomly, and they're independent groups, and my sample sizes are both bigger than 30, which means I'm allowed to assume normality. Quick run through of the conditions. But now, is there evidence? That means I have to do a hypothesis test, even without that explanation there. Which means that step 1 is, of course, state the hypotheses. I wrote that weird, but whatever. On your formula sheet, you can build a confidence interval. You can do a hypothesis test. Same thing as before. With the 2 groups, you've got 2 options. Just pick whichever one you prefer, right? And so you could say mu p is equal to mu m, or mu p minus mu m is equal to 0. Right? Those are equivalent statements. But you do have to use question-specific subscripts in your hypotheses. Huh? And so the null hypothesis, mu p is equal to mu m, or if you prefer, mu p is, minus mu m is equal to 0. Those say the same thing. Just depends on how you want to think about it. Your alternative hypothesis should reflect what we want to test. And so our platypuses, even slower than manatees, would be a mu p is less than mu m. Right? They're slower. Yeah. Slightly harder if you use this version, right? Because if mu p is consistently less than mu m, then I would get a difference that's less than 0, right? I would get a negative difference. And so that's the reason I don't really like this version. I think it's harder to wrap your head around, but it is technically the point estimate, or where the point estimate came from. So who am I to say? Oh, but just pick one. And I've written it down so many times, but must use question-specific subscripts in the hypotheses. You don't have to later in the T, right? Because it gets really messy. Well, but you do have to in the hypothesis. Well, this is a one-sided test. I'm only concerned about the platypuses being significantly slower than the manatees. If we find evidence that that's the opposite is true, then I don't care about that. Right? And so this is a one-sided test. Step 2, do the test. Your test statistic is still a t, right? We know how t's behave, which is really nice. And so t, just how we get there is a little bit bigger, but t is going to be x1 bar minus x2 bar. Technically, this, I don't think this part's on your formula sheet, but minus mu1 minus mu2. But it's not on your formula sheet because we assume the null hypothesis is true. So then we assume that this difference is 0 always. That's why it's not on there. But technically. And divided by the square root of s1 squared over n1 plus s2 squared over n2. You don't want to forget about those squares. The squares are only on the s's, right? And then you don't want to forget about the square root, right? There's kind of lots of different calculator errors that you could make. So just be careful. Oh, x2 bar, sorry about that. Okay. Now, I need my x bars, 3.6 minus 3.9. As long as you kind of keep your groups, group 1, group 2, then you're okay. Notice I'm not using question-specific subscripts here. That's okay, just for your hypotheses. They still refer to the same groups, though. 3.6 minus 3.9 divided by, and what, 3.1 squared divided by 200, 2 plus 2.8 squared divided by 156, I think it is. Okay. Now you don't have to show your work here, but you do have to do it nice and slowly. So I'm just gonna 3.1 squared divided by 200, and I'm gonna store that. And then 2.8 squared divided by 156 plus recalling. Just so you can check in, you should get, and then the square root of that in the denominator, because that's where I started, 0.313538537. 3.6 minus 3.9 is negative 0.3 divided by that guy. I get a t of negative 0.956820201 to 3 decimal places. Unless someone else got something different. Well, I thought I did it carefully, but then I always second guess myself. 0.957 to 3 decimal places. Now I need to find my p-value, step 3. Already though, I have a feeling I will not be rejecting H naught. Right? T is not even close to being -2 or +2 on either end. And so I suspect I won't have enough evidence to reject H naught, but we use the p-value for formality. Find the p-value. Well, using the t-table, since I calculated a t with degrees of freedom equal to the minimum of n1 minus 1 and n2 minus 1, right? That's on our formula sheet. So then the degrees of freedom is the minimum of 200 minus 1 or 156 minus 1, which is the minimum of 199 or 155, which is 155. But I already know I'm not going to find a 155 line on my table. But let's see what we've got. So I have 155 degrees of freedom. I'm choosing between 100 and 1,000, but I have to use 100, right? Because I can't round up. So while I'm here, may as well copy. So then I say, but using degrees of freedom equal to 100. In real life, you would use software, Excel or R or whatever. Then you can use 155 degrees of freedom. Or you could even get fancy and calculate the actual degrees of freedom. But since we're using the table, we have to use 100. That's all right. Our calculated t, the absolute value of negative 0.957 is between 2 values. So if I try to place 0.957 somewhere here, I end up here. So 0.845 and 1.042. Now, we have a one-sided test, right? Because I want to know if it's less than. So I need a one-sided p-value. So my one-sided p-value is between 0.15 and 0.20. Make sure you read those from right to left, right? Or list them from smallest to largest. Just as we suspected, again, right? Time for our conclusion. And to keep it on this one page here, maybe I'll bump this up. Step 4, your conclusion. Same as always, right? Since our one-sided p-value is between 0.15 and 0.20. I'm going to scroll. I have a feeling we were given an alpha level to use. We were, and it wasn't 0.5, so, but still, it's not going to be less than 0.1 anyways. And so between 0.15 and 0.20, since our one-sided p-value is between 0.15 and 0.20, it is not less than our alpha level. Whoops, can't write anymore. Our alpha level of 0.10, which means we do not have enough evidence to reject H naught. Do not have enough evidence to reject H naught. Oh. And then reword the question as an answer. Is there evidence that platypuses are even slower than manatees? No, there is not. Therefore, there is no evidence that platypuses are slower than manatees. Oof. How about a confidence interval? Making me work for it. Because we already did, can I change this question a little bit to something more reasonable? We just did the hypothesis test. Do you think that a difference of 0 is going to be in the interval or no? From our hypothesis tests, I would expect a difference of 0 to be in the interval, right? Because that's a potential outcome, right? And so instead of kind of using this question here, I guess I'm crossing it all out. And instead, just scrap it all. Construct a 99% confidence interval more in line. So this question is kind of more in line with what I would expect you to do for a confidence interval. I do need you to be able to use a confidence interval to check a hypothesis. But construct a 99% confidence interval for the difference in mean speeds of platypuses and manatees. There. Ah, we can do. X1 bar minus X2 bar plus minus a T star critical value times that same square root. Now, if I had been clever, I would have stored that square root in my calculator. I did not. Forgot. Whoopsie doopsie. S1 squared over N1 plus S2 squared over N2. Here we go. I wasn't ready. I need my T star. T star at 100 degrees of freedom. At degrees of freedom equal to 100. Now, technically, I should be writing out how I calculate the degrees of freedom. Fine, I'll do it properly. Man, I'm such a stickler with myself. I'm gonna put it above though. Need T star at degrees of freedom equal to the minimum of N1 minus 1 or N2 minus 1. So the degrees of freedom is the minimum of 200 minus 1 or 156 minus, whoops, minus 1, which is the minimum of 199 or 155. So the degrees of freedom is 155, but using degrees of freedom equal to 100, that's the same blurb as we did earlier, but let's pretend it's a new question. That's what I was trying to shortcut. T star, the critical value for a 99% confidence interval. So we still have 100 degrees of freedom, and I want to find 99 here. Whee! 2.626. Just trying to not write out the formula again, but can't be helped. 2.626. Okay. The difference in the means is the same as before. Just gonna write it out here. In fact, that was a long scroll away, so I'm just gonna copy this. Bring it down. (3.6 minus 3.9) plus minus 2.626 times the square root of 3.1 squared over 200 plus 2.8 squared over 156. Here we go. One, 6 plus we call A. Square root that times 2.626. I get a margin of error of 0.8233521817. Negative 0.3 minus that guy puts me at negative 1.123 to 3 decimal places, up to negative 0.3 plus that guy. 0.523 to 3 decimal places. Oops. Now, if you've made a confidence interval, you have to interpret it, right? But we use the same blurb as always. The key here, though, is that we're talking about the difference in the means, right? And it says on your formula sheet as well, just to kind of nudge you in the right direction. So the difference of two means as opposed to paired data where it's the mean difference, right? And so words really matter. I know. Makes it more fun though, right? We are 99% confident the interval from negative 1.123 to 0.523 captures the difference in the mean speeds of whatever I was asked to build, captures the difference in mean speeds of platypuses and manatees. Captures the difference in mean speeds of platypuses and manatees. Okay. As a follow-up, we can answer the original question, right, by seeing if a difference of 0 is in this interval, right? Because my point estimate is for the mean of group 1 minus the mean of group 2, then we could test the null hypothesis that mu p minus mu m is equal to 0. Or the alternative that mu p minus mu m is not equal to 0. Another reason to skip it, because a confidence interval does a two-sided test. But what you want to look for is if 0 is in the interval. Okay? If it's in the interval, that means you don't have enough evidence to reject H0. It's a perfectly reasonable result. Right? Let's see if I can squeeze it in here. Since 0 is in the interval, we do not have enough evidence to reject H0. To reject H0. Tight. But I don't want to do a full page just for that. And then, of course, the conclusion matches what we found with our formal hypothesis test. Nice. Okie dokie, artichoke. Any questions about that one before we do the sort of last one?
Is that one also going to be 3 marks?
So confidence intervals, I tend to do 4 marks.
Oh, no, just for the conclusion.
It would be if I asked, yeah, if I asked you to do it, but then because I changed the question, and I just asked you to make a confidence interval, then it's just 4 marks and you don't have to do the conclusion. This part in light blue, I'm just adding it just extra. I'll write extra here. Because I changed the question to be a little bit easier. But then I did it anyways, so I should have just left it. All right. Last one. I think it's the easiest one, so that's nice. Here we go. We decided it was a one sample mean. In fact, we've already practiced a one sample mean type of question, right? It was the special case of the paired data, right? But all our calculations stay the same with the exception of one thing. Right now I have a number that I want to compare my mean to. So you would like to estimate the mean amount of material a platypus stores in their cheek pouches. You collect a sample of 40 platypuses and measure the amount of material each of them store. You find the average to be 33 grams and the standard deviation to be 5.3 grams. So let's jot down the information that we're given here. N is 40. X bar is 33 and your S was 5.3. Yeah. Now, part A. Which is more in line with how I tend to ask questions. You've heard that they store 30 grams on average in their cheek pockets, but you suspect it might be more than that. Is there evidence to support your suspicions? Use an alpha level of 0.01. So here it doesn't explicitly say use a hypothesis test, and so this is more what you can expect the question to look like. But you do have to use a hypothesis test. So here we go. What's this 30? 30 is the number I want to compare my sample mean to, right? Which is what makes it my mu naught. Huh? Step 1, state the hypotheses. Okay. From your formula sheet, right? If you're doing a hypothesis test, step 1, state your hypotheses. Mu is equal to mu naught. So you have to replace the mu naught and the p naught for proportions. Those are just placeholders, right? Number from the question. So you want to have mu is equal to 30. Right? Mu naught is 30. And the alternative hypothesis, you suspect it might be more than 30, so you suspect mu is greater than 30. But you have to assume it is 30 until you have evidence that it's greater than 30. You only care about the one side, so makes it a one-sided test. And page here. Step 2. Do the test. Do the do. Step 2 on your formula sheet, right, is calculate the t, the test statistic, x bar minus mu naught over s over root n. And of course, our degrees of freedom is n minus 1. So our t in this case is 33 minus 30 divided by what was it, 5.3 divided by the root of 40. How far is 33 from 30, taking into account the standard error? Here we go. 5.3 divided by the root of 40, and then 3 divided by that guy. Whoo, that's exciting. Get excited when I get to reject the null hypothesis. 3.5799366974. I expect to reject the null hypothesis with such a large T. That's really telling me that 33 is really far away from 30, right? It's really high above 30. So to 3 decimal places, 3.580, I guess. Step 3. Find the p-value. If you've calculated a t, you have to use the t-table, which means you have to have your degrees of freedom. So, using the t-table with degrees of freedom equal to n minus 1, that's on your formula sheet, right? Which is 40 minus 1, which means your degrees of freedom is 39. I already can tell I'm going to have to use something else, but what? Well, I know, because I feel like I know all the degrees of freedom by now. If I have 39 degrees of freedom, then I have to use 30, right? 30 degrees of freedom. So I say that, but using degrees of freedom equal to 30. Then we can get to work here. The absolute value of t equal to 3.580 is between two values. It's going to be between, let's see here, 3.580, we're inching towards the end. Even if it was on the right-hand side of 3.646, you know what to do there, right? Then it's between 3.646 and infinity. Right? In this case, it's not. We're still on the table, 3.385 to 3.646. Now, I seem to remember we have a one-sided test because I want to know if it's more than 30. So it's a one-sided p-value is going to be between something very, very small. 0.0005 and 0.001. Very, very small. Time for our conclusion. I'm cutting it close, I know. Still have time though. Just going to remind myself, use an alpha level of 0.01. It's still less than 0.01 though. So here we go. Since our one-sided p-value is between 0.0005 and 0.001, it is less than our alpha level. It is less than our alpha level of 0.01, which means we have enough evidence to reject H naught. Which means we have enough evidence to reject H naught. And if I'm rejecting it, I tend to say in favor of HA. You don't have to, but I tend to. Therefore what? There is evidence to support my suspicions that they store more than 30 grams on average in their cheek pockets. Therefore, there is evidence to support my suspicions. They store more than 30 grams on average in their cheek pockets. Ah. Oh. Nice. How much more is usually the reason we build confidence intervals is, okay, great. We know that they store more than 30. Well, then like how much would they store? It's kind of useful as well. So confidence interval, here we go. Give a 90% confidence interval for the mean amount of material a platypus stores in their cheek pouches. We need, right away, I'm just going to jump into it in the interest of time. We need T star for degrees of freedom equal to n minus 1, which is 40 minus 1, which is, pretending we haven't already done this, 39, but using degrees of freedom equal to 30. For a 90% confidence interval. 90%. Oh, just looking at my p-values thinking, why did I highlight the p-values? I didn't need to, that's all. T star is going to be 1.697. I will point out that at an alpha level of 0.01, for a one-sided test, the equivalent confidence interval would use a critical value of 2.457. That's beyond what we need. You've been asked to make a 90% confidence interval, but it might not necessarily match what we found in our hypothesis test because they're not the same. Okay, here we go. X bar plus minus T star, because I already did it, times S over root N. X bar was 33 plus minus, what did we find? 1.697 times 5. Now I lost it, 5.3, I think. 5.3, so close. over the root of 40. It's a nitty-bitty calculation compared to what we were doing. Times 1.697. I get a margin of error of 1.422092075. $33 minus that guy puts me at 31.578, and 33 plus that guy, 34.422 to 3 decimal places. If you build a confidence interval, you have to also interpret it, right? And so here, for these 4 marks, this would be 1 mark, or 1 mark, 2 marks. It's not much better. And then the interpretation, we are 90% confident the interval from 31.578 to 34.422 captures what? Whatever we were asked to make an interval of. Captures the mean amount of material a platypus stores in their cheek pouches. The mean amount of material, now I lost it, a platypus stores in their cheek pouches. And this is 2 marks. Last tiny bit. Discuss what it means to make a type 1 and a type 2 error in the previous question. Thought you were done with those, right? A type 1 error is what? When you reject H naught when you shouldn't have, right? And so reject, or maybe I'll do the generic one here. Reject H naught when we shouldn't. That would be an error. And a type 2 error is fail to reject, fail to reject H naught when we should reject it. Type 1 error. In this scenario, what does it mean in the previous question? Is claiming they store more than 30 grams in their cheek pouches when they don't, right? So claiming they store more than 30 grams in their cheeks, let's say that, when they don't, that would be rejecting H naught when you shouldn't have, versus a type 2 error in this case would be claiming they store 30 grams when they store more than 30 grams. They store 30 grams when they actually store more. More than 30 grams. You made it. If you have any questions, let me know. Otherwise, I'll see you for the test on Tuesday. I hope you enjoy your weekend of studying. Presumably.